There we go. Okay. Well, I started the tablet and got it all set up, and then it wanted to reboot. What do you want? It's Windows. It always wants to reboot. So anyway, hello. I am Scott Grizzard from the University of South Florida. Let me throw my title down there. There we go. It's behind me again. Very nice. And this is Discrete Math. What is today anyway? The 3rd of September, 2020. Today is lecture, I think I got it wrong when I put it on the thing. So today is lecture 2B, second lecture, second week. And today we're going to be talking about, and today we will be talking about why I can't find what we're talking about. There we go. Set operations, and we might get to functions. I wanted to talk about logic, but I think I'm going to push that to the next thing so it's all together. As usual, let's say hello to everyone in Discord chat, where you may chat if you don't want your information shared publicly. And there's also Twitch chat, which is that way, which you can use if you don't mind the fact that everyone can see the questions you're asking. So hello. And yes, again, today we have a TA. Yes. In chat. Are there any questions before we begin? Yes, one announcement that someone's already posted in Discord is that the retakes are up. I got that fixed. So, are there any other questions? Right. So the way that the quizzes retakes work is that it's for half the points you missed. They are at the bottom of the assignments because they don't have a due date. Whether or not they get a due date or not, of course, I'll tell you in advance if they do get a due date. But what's going on there is that the retakes are, you have to take them on paper. And then when we grade them, we change your original grade. So you don't get like a grade for the retake. We change your original grade, leave a little comment that said we changed your grade. And that's it. But you have to take them on paper and then scan them and upload them, all using Proctorio. The instructions are in there. You'll see it. It's rather straightforward. The reason they're on paper is because it's hard to get the silly system to work right otherwise. All right. So are there any other questions? What is I actually read the syllabus assignment. If you actually read the syllabus, you'll find out. Any other questions? All right. And all of you who are protesting that says you read the syllabus and still don't know it. Yeah, but you read the syllabus in the same way that I, read the directions that came with my cell phone. I just turned the thing on and put in my Google password. So, came with a little instruction manual that was that thick and out that went. So, actually read it. Any other questions? Yes, you could direct message me or come to office hours or bother me in office hours at 12:30 tomorrow, which are, of course, on both, not office hours, the coding help session, which is on both Discord and in person, as long as we have decent weather. Any other questions about that? Okay. So let's start. We'll talk about the quiz first. There it is. So some people either had problems with this quiz or you didn't. Some people are still a little bit unclear about what subset means. So on next week, when I start the logic stuff, I'm actually going to talk about formal definitions of these things, and we'll work a couple more examples. So 2 to the B is, of course, the power set. So it's the set of all subsets. And of course, there's 4 elements. There's 2 elements here, so 2 squared would be 4, so there's 4 elements in this, right? I've got an empty set, a set containing 0, a set containing 1, and a set containing 0, 1. B choose 1 is the set of all 1-element subsets. The collection of all 1-element subsets means that it has the set, the singleton 0, and the singleton 1. And A cross B is, well, the set of ordered pairs. So I've got A0, B0, C0, that is a C, A1, B1, C1. How do we feel about that question 1 to 5? Okay, we apparently have a dead bot in Discord. So, okay, well, people are posting their things. That's fine. I think we'll get another bot going or something like that. There is another bot that you can use besides that one, but you can you'll figure it out. Anyway, we got a dead bot. Anyway, that's what happens with poll bot. Sometimes it disconnects, but it is kind of the simplest one. The other one that I had the other bots kind of leave ads and stuff. I didn't want them on our Discord. So, okay. Anyway, we still feel pretty good about that. This one was a little trickier. So we got a deck of cards. Yes, I have a deck of cards. Of course I've got a deck of cards. I've got several decks of cards. In fact, you know I teach discrete math because I have a box. I have a set of sets of cards, right? It's a giant box full of them. That's how you know you're a discrete instructor. You just got cards. You have cards because you have to have cards to do discrete, right? You have to have cards to think about discrete. So we've got a deck of cards. How many ways are there to deal? How many ways are there to order the clubs? So I can go the classic order, ace through 10, jack, queen, king, but I could flip the queen and the king. That'd be a different order. There are 13 cards. That means there are 13 factorial ways to order them. 13, right? I pick the first card, and then I pick the second card, and then I pick the third card, and so on and so on and so forth. How do we feel about that one, 1 to 5? Okay. Very nice. All right. Now, how many ways are there to deal 3 cards with the order matters? From the whole deck. Nope, that's my bad. That's wrong. From the whole deck. Of course, I made a mistake right there. From the whole deck, right? So there are 52 falls 3, right? Because this can be the first card, this can be the second card, this can be the third card. Any questions? Okay. All right, how many 5-card hands are there in total? So I'm asking how many 5-card subsets are there? How many 5 subsets are there of the 52-card set? And the answer is there are 52, choose 5. Okay. So how do we feel about A, B, and C1 together, 1 to 5? The basic question is about whether or not we understand what the different notation means, really. All right. Someone had another bot up there. That was nice. Okay. So some of us are a little, we're not quite sure, but that's okay. We could talk about it. If you're having trouble with the notation, come see me. Which one's which one is in order. It has to do with the wheel of multiply. And we can talk about it. All right. So there are 12 face cards, right? There are the Queen of Hearts, Queen of Diamonds, Jack, Queen, King, 3 of each suit. There are 4 suits. That gives us 12 cards. So how many 5 cards hands contain only face cards? Well, 12, choose 5. And if you wanted to determine the probability of getting all face cards, if you got 5 cards, it would be 12, choose 5. 12, choose 5 over 52, choose 5. And I'm sure that face that I just made while I was trying to get tongue-tied will become a clip. All right. So how do we feel there about C2, 1 to 5? All right. So I take the number of total number of face cards, and it's just, I get 5 of them. All right, now here was the hard one. How many hands contain exactly 1 king? And the way to think of this was that I pick what's the king, right? So I've got, in the deck, there are 4 kings. I want 1 of them. So 4, choose 1. I pick which king I got. And then I pick the other 4 cards. Well, I don't want any other kings, right? So there are 48 cards left with no kings. And so after I've chosen the king, I pick the other 4 cards in the hand. And that gives me 4, choose 1 times 48, choose 4. Okay. How do we feel about that? That one was a little trickier. All right. Okay. So the idea was I picked one and then I picked the other. And I said and then in between, so I multiply. This can get you into trouble, right? Because if what you wanted was, you know, all the pairs, all the decks where you were picking 2 of a kind, right? So, you know, you'd pick how many, you know, how to pick the 2s and then how to pick the rest. But it depends. Do you want, you know, the 2s with the do you want to exclude 3 of a kind and so on and so forth, and do you want to exclude 2 pairs? So these things can get tricky. Yes, those 2 things are multiplied. 4, choose 1 times 48, choose 4. Should be a little dot in between them to indicate the multiplication. Okay, and I don't know why this says first lecture. It should say last lecture. But, you know, the previous lecture. But it, because I'm lazy and I keep copying the question off the first one, I'm keep winding up with the same thing. Yeah, I keep saying it on every quiz. It's supposed to be in the previous lecture. I suppose the last lecture you wouldn't be able to tell me because we haven't had it yet. But yeah. All right, are there any questions? Okay. All right. Let's talk about what we're going to talk about today. So last time we talked about the counting principles and we got to this cross product thing. Today we're going to kind of expand on that, the other set operations. So we've talked about power sets. We've talked about some other, some sets of sets and some special sets. But we want to really talk about what happens when we combine 2 sets and how we can combine 2 sets and how we can deal with 2 sets. Let's move this over here. And yes, there will be Venn diagrams today. Those are always popular, I know. There will not be truth tables today. We will wait on those. Okay, so the idea is, and all the sets we're going to deal with today, we're just going to assume they're finite. The rules don't really, it doesn't matter whether they're finite. The nice thing about them being finite, though, is that that you can just keep taking intersect. I'm not talking about taking an infinite number of sets and intersecting them. I'm just talking about taking a finite number of finite sets and a finite union of finite sets, and doing those things. And we'll also talk about something called the direct sum. Some people call it the smash union. Some people call it the disjoint union. That's another name for it. But it is something that you can see in operate. So it's not a very popular thing as far as sets in mathematics to talk about direct sums, but it actually is one of those like esoteric things that nobody cares about. That's actually very practical when it comes to things like databases and counting those. So we'll talk about it. As I said, not many mathematicians care about it, but it is kind of one of these little useful things when you're thinking about a database in a weird way. This corresponds, by the way, roughly to oh bother. What's this book called? Oops, I closed the book. This this roughly coincides with the rest of chapter 2. In what is that? Han and Koppelers, or however he pronounces his name. In Han and Kopp. So in that book, Applied Mathematics for Database Professionals, this is the rest of 2. And I will post. So did everyone see that I posted exercises as requested at the bottom of the notes? If I posted the notes, I don't remember if I did. But so at the before I posted the notes, I added some exercises to the bottom. And you can see those if you go over to the notes on Canvas from the last time. I assigned a couple. People were asking for them, so I did some. Okay. All right. Yes. So we'll put that comment in there. I said finite an infinite number of times. You know, they've got that counter thing. I don't know if you've seen that on YouTube. Maybe I'll do that, right? Every time he says finite, count it. You know, ding, ding, ding. So, whatever. Fun. All right, so let's let A and B be finite sets. Actually, we don't even need them to be finite. They can just be sets. The point is we've only got 2 of them. A union B equals X in equals the set of elements X such that X is in A or X is in B. Translation. We take the stuff in A, throw in the stuff in B, and call it a new set. Right? So we just took all the stuff in A, we took all the stuff in B, we lumped them in together. Okay, so example. Let A equal AB, B equal BC. That means A cup B or A union B. This is sometimes called cup. We'll say this is union here. Equals A, B, and C. Right, because B's in both. Okay, so B's in the union, but A's in one, so A's in the union, B is in one. So C is in one, so C is in the union. How do we feel about that 1 to 5? I think I'm required by contract to do a Venn diagram. Nope, that's too. What light pencil? How do I do light pencil here? Oh. Nope, too dark. We'll do highlighter. It's taking me longer to draw this Venn diagram than it actually does what you care about, right? So here's the Venn diagram. There's A, there's B. I want everything together. All right. Lists are a little different. So unions of lists are a little different, and I will get to that, but they're not quite the same. We need a technical term for a list, and we'll get to that. We might get that today, or we'll get that or we might get that tomorrow. But a union of a list, it's not quite the same thing, because what we want back is a list. And so we can concatenate lists. That's an operation on lists that doesn't really apply to sets, because we want and we can smash lists, but we can't really union a list in that way. And as I said, I'll explain about, once you understand what a list is, you'll understand why it's kind of hard to do that. You kind of need an operation on a list. But that's a very good question. A list can have a duplicate, but a set doesn't. It's not like, a set would not know the difference between A, B, B, C, and A, B, C, right? They're all the same set. So, you can write A, B, B, C, but it's not technically wrong, but it's wrong because people would be like, you don't understand what a set is, right? You write it in its simplest form. You don't understand what a set is. So if you did that on a quiz and something, I would mark it wrong because the indication is you don't know what a set is. Any other, right? Because remember, A, B, B, C is the same thing as A, B, C. All right. We have the intersection. Okay, and the intersection, A, sometimes called cat B, equals X, such that X is in A and X is in B. All right, you're never going to remember that. Remember the picture. Here's A, here's B, and the intersection is the bit in the middle. So, all right. The next one is the difference. So the set difference is defined. So A minus B equals X in A so that X is not in B. So from before, okay, so A is in A, but not in B. B is in A, but it is also in B, so I can't use it. C is not in A, so it doesn't get in at all. So here, A minus B equals A. there any questions about that? No, so the difference is not whatever's not in both. This is the things in A that are not in B, right? So it's A without the intersection of A and B, or just A without the stuff that's in B, or the stuff that's only in A. Are there any other questions about that? That's a good question. Oh, yeah. That's an ampersand. I got lazy. I shouldn't do that. Anything else? Okay. There's one more, and it depends. It's usually called the symmetric difference. I'm going to put this as an aside because I'm not going to ask you, because it's not that it's useless. It's just, it's not really, you don't need it because you can define it in terms of the others. And it's a little confusing on its notation. Let me see which one that this book uses. I think this book uses the division sign for it. Substitution, hybrid, predicate method of specifying sets. Yeah, it's using the division operator. All right. I just wanted to check to make sure it was this. I was using the same thing. So this is the symmetric difference of A and B, and that equals A minus B union B minus A. Okay, so it's basically the stuff that's not in the intersection. Another way of writing this is to say it's A union B minus A intersect B. They're the exact same things. And if you look at the Venn diagram, you'll see this. And it's, again, this one's a little weird, and you don't need it because you can express it in terms of the others. But some things have it, so I'm just sticking it in there just in case you wind up seeing it in another class. And that's what that means. I'm not going to ask you about this, but just in case you see it one day, it says confusing, not confuse. Warning, confusing notation. Basically, the division operator was left over when they did a bunch of these things, and they're like, oh, we'll just use the division operator, the division symbol. Okay. So, I mean, you actually see that in programming all the time, right? Where you've got a whole bunch of operators. This is like normal in Java, right? You want to define the operators for your special objects and stuff. And people define operations on their objects, and they use the symbols like concatenate when that means something totally different. And the same thing happened here. The division symbol was hanging around, and they're like, oh, we can use the division symbol for this. Good for them. All right. Okay. Any questions about that? All right, so those are kind of the big things. Now, how do we count them? Well, in a sense, we can't, okay? But we can do stuff, we can say some things, right? So, A union B. Well, that's not the same thing. I don't take, so, cardinalities of these things. So, the first thing we can say is we don't get clean things, right? So, for instance, the size of A union B, we know that it's less than or equal to the size of A plus the size of B. But we can't say anything more, right? Because we don't know, right? We know it's less than that. We can, however, we can say a little bit more, right? Because if I take the sets, so let's say I take these three cards here, 6, 7. I swear, they are not in order. I don't know why 6, 7, 8 just came off the top. Somebody calculate the probability of that. And then if I take the cards, the 6, 7, 8 of... So if I take the sets hearts, I say one set's the hearts, and the other is the eights. Okay? Well, hearts union 8, right? There are 2 8s, and there are 3 hearts. But heart union 8s has 4 elements. Are we on board with that? And we know... So we know that it's less than or equal to. We also know that A intersect B is less than or equal to the maximum of these two sizes. All right. Now, if I know one of these, if I know A intersect B, I can actually get at A union B. If I know A intersect B, then I know that A union B equals the size of A plus the size of B minus the size of the intersection. Right? Because I know that there are 3 hearts, and I know that there are 2 8s. And I know that there is one 8 of hearts. So I know how much I've double counted by. Does that make sense? I know how much I've double counted by. So I know that when I count A plus B, I've counted one card twice. So I simply subtract out the one I double counted by, and I wind up with the size of the union. How do we feel about that? 1 to 5. So, I mean, I did do an example, but, right? So, example. Hearts, right? 13 cards. Kings. 4 cards. That means that the size of hearts union kings is less than or equal to 17. And since I know, right? And I also know that the size of hearts intersect kings is less than or equal to max 13.4. So I know that hearts intersect kings has to be less than 4. All right, now, if I know hearts intersect kings equals 1, then I know hearts union kings equals hearts plus kings minus 1. Right? So I know that this is 13 plus 4 minus 1. Excuse me. Or in other words, I know that there's 16 cards that are either hearts or kings. The union of hearts and kings is 16 cards. How do we feel about that, 1 to 5? Oops, sorry. Okay. And now my head's in the way again. All right. So let's come back here. And this method, I can actually expand this method. All right. So let's expand this method a little bit. And let's talk about A union B union C. So now I have 3 sets, right? Which is the same. So really what I have is 2 sets, except now I have, 3 sets. I'm talking about 3 sets, but I could think of them as 2 sets. So this is what I mean by a finite union. Okay, so I've got 3 sets, and now I'm just going to talk about how big they are. Okay. All right. Okay, so I know it's going to be less than or equal to. This is kind of obvious. Okay. But I want to get a better answer. So the better answer, I'm going to treat A union B as its own thing. So the size of A union B union C, which would be the same thing as going the other direction. But we're going to apply our formula by plugging A union B in for A. So my formula before was, I'll put my formula here, S plus T, S union T equals the size of S plus the size of, and I know I'm in front of it, plus the size of T minus the size of S cap T. All right, so I know that from before. So now I'm going to let S be this A union B business. And I'm just going to apply the formula again. So I wind up with A union B plus the size of C. I'm just applying the formula here. Minus S, which is A union B, intersect C. All I did was apply this formula to that, treating A union B together as S. All right. Now, the size of A union B, so I'm going to take this now and sub it in. And the size of A union B equals the size of A plus the size of B minus the size of A cat B. That's this. Plus the size of C minus. Now I've got this A union B here intersects C. Let's hold on to that for just a moment. All right. How do we feel about that? Okay. All I've done is I've applied this formula to that. So on the first run, S equals A union B. On the second, S equaled A, T equaled C. And on the second, S equaled A, and T equaled B. So all I did was apply the formula to the set that is the union as S. So I just kept it all together. All right, let's talk about this thing. I've got three sets. I've got A, B, and C. And I want the stuff that is in, I want the stuff in where? In A or B that is also in C. So I can write this I want the stuff that is in A or B, but is also in C, which means I could write this as the stuff that is in A intersect C union B intersects C. Okay. In other words, what I wanted was all the stuff in A and all the stuff in B together. That's also in C. Well, I can take all the stuff that's in A and C and all the stuff that is in B and C and just union them together. And that will give me the same thing. All right, I'm going to pull this over because that's settled, and I'm going to keep this here. So I'm going to do A plus B plus the size of C minus A intersect B minus the size of A cap C. Oops. No, I don't want that. I want this. A cap C union A cap B. Ugh. Now I apply the formula again. And I wind up with A plus B plus C minus A cap B minus... Okay, now I'm applying the formula. So now S equals A cap C and T equals A cap B. Or, I'm sorry, B cap C. This is wrong. Okay, so let's apply that. So I'm going to write this here as the size of S, which is A cap C, plus the size of T minus the size of A cap. I'm sorry, no. S cap T. Right? Where these are the things that they're equal to. A plus B plus C. I love your guys' comments. Minus A cap B minus the quantity. Okay, so I've got, for the size of S, I've got A cap C. Plus the size of T, which is B cap C. And now I've got something interesting. What is A cap B cap B cap C? So what is the intersection? This asks, what is, this asks for the stuff that is in both A and B and in B and C. Well, that's just A cap B cap C, right? I want the intersection of all the stuff that is in A and B with the intersection of all the stuff that's in B and C. What's left? Well, that means I want the stuff in A that is also in B, that is also in B, that is also in C. All right. I'm almost done, guys, with this little line, and then you'll be happy. All right, now I'm going to distribute my negative. And look what happens to that last intersection. Okay? Now, let me ask you something. Could I go on forever if I wanted to do 4 or 5 or 6 or 7 or 8 of these? And the answer is yes. I could keep going and going and going and going and going. I can expand this formula using my original 2 formula the points. 1, I can use my original 2 formula over and over to compute the size of any finite number of intersections of unions, as long as I know their intersections. And the technical term for this is recursion. And we're going to come back to it. It's going to be something that we're going to see again. 2, this is a pain in the ankle. And that's one of the important things about this, is that there's no real better way to do this. And if you want a computer to do it, it'll do it. And it'll do it recursively. Okay? So it will compute these things for you. But it's going to do it again and again and again and again and again. So the number of steps that you now have to do gets huge once you start talking about big numbers. Because you have to compute, right? If I want to calculate the size of the union without duplicates of a whole bunch of stuff, right? Where I've got table after table after table after table, right? If I want to do that, it's going to take the computer time, because the computer has to compute all of these intersections by doing a match, by doing a join. Each one of those intersections is an inner join when you do it. Okay? The computer can do it, and the computer can do it using recursion, and the algorithms for doing it are beautiful. But computing these things is a pain in the neck. Okay? For the computer, even. You're better off getting an estimate of this, right? So there's a reason why you don't want the exact formula. There's plenty of times when just having the formula, just having an approximation is close enough. Okay. And that's the point, right? You want to make sure that if you're doing this, right, it's kind of the point of this math, right? You want to learn the math so that when you're programming your own code, you don't thrash your database and do queries that take 3 days to compute. Right? Okay. Let's do an example of this. This, by the way, is called the Sieve. I think that's how you pronounce it. This is called the Sieve. So, and if you think about it, what you're doing, right? If I had 3 of these sets, A, B, and C. So I've got the set of red. Oh no, those are subsets of each other. I have the set of red cards, the set of I can't really come up with 3 at the top of my head. So I've got the set of red cards, the set of, let's just pick some. So I've got the set of cards I pulled out of this pile. And in there I have a, and then I've got the set of red cards of the whole deck. And then I've got the set of face cards from the whole deck. So I've got A equals my pile. B equals face cards from whole deck. Oh, I didn't want to use that color. And I've got C, which equaled the red cards from the whole deck. Yeah, we'll do the hearts. Why not? This is an example. Okay, so I want to know how many cards do I have together? Okay, well, if I just count them, right? If I run this here, now, if I do A plus B plus C, I've overcounted. How do we feel about the fact that if I do A plus B plus C, I've overcounted? Okay. Now, what I'm going to do is then I'm going to subtract the pairwise intersections. So I'm going to subtract pile and face. And I'm going to subtract pile and hearts. And I'm going to subtract hearts and face. Now, how do we feel about the fact that now I've taken away too much? Right? I overcounted the first time, but now I've over-subtracted in a sense. I'm closer, but I've kind of over-subtracted. Because I subtracted out one set twice. I subtracted out all the cards that were in my pile and hearts and face. So I subtracted out one. I subtracted out one set to me. When I took away from my counting, I took away a little bit too much, so I have to add it back in. So now, what do I need to compute? I need to count the number of cards I have. That's easy. But now I have to compute this, this, and this. So let's say my pile had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let me make sure I've got some hearts and some face cards in here. I've got some face cards that don't have any hearts. There we go. So 1, 2, 3. We'll put this back. All right. So I've got my 10 cards here. Now, what all do I need to compute? Okay? So in order to actually get the number, I need to know my pile was 10. How many cards are face cards from the whole deck? 12. Right? And then how many cards are hearts? 13. Now, I need to subtract all the cards that are in my pile but face cards. So let's see. I've got the King of Diamonds, the King of Clubs, the two Jacks here, Jack of Diamonds and Jack of Spades, Jack of Hearts. Okay, so I need to subtract all the face cards from my pile. There are all the face cards. There's 6 of them. There are 6 face cards in my pile. Now I need to subtract the cards in my pile that were hearts. Now, notice that I'm over subtracting, right? I already counted these 2 cards as over counted to begin with. So now I've taken 2 cards out too many. And I need to subtract all the hearts and face cards. So how many face cards are hearts? 3. Now I need to add in the 2 hearts face cards in my pile because I over subtracted them. I counted these twice when I did my subtraction. So because I counted these twice when I did my subtraction, okay, for some reason this charger's not working and my computer wants to shut down now. Give it the real charger. All right. I need to add those 2 back in. Now, so now I can do the thing, right? And do that. So I've got 3, 3, 6. This is going to be a minus 12. That's going to be a plus 2. This is going to be a 10 plus 12 plus 13. The 12s are going to cancel. So we wind up with 15. We wind up with 1525. Okay. Now, how many things did I have to compute? How many things did I actually have to manually count? All right. 1, 2, 3, 4. Okay. And remember, each one of these is a join. So imagine if your table had 5,000 rows. Right? This could take a little while for a computer. How do we feel about that 1 to 5? All right. So the point is I don't want to do this. Okay. Let's see. I did unions, intersections, differences. We counted them. We did the cross product last time. There's one more, and it's called the direct sum or the smash union or the thing. Okay. So let's go ahead and do that. So we did cross product last time. Okay. And we also did, and we also talked about k-tuples, which are k runs of this. Okay. Here's the new one. And the way this is written varies. Usually you see something like this. Or you may see like this or something like that. I'll actually just use that. So the union with a plus inside is the set of A together with B where I keep track of where each element came from. All right, so that's a little weird. Let me give you an example, and you'll see it. Now let's do A, B, and B equals B, C. All right. So what I'm going to do here is I'm going to do A cross B. So what's A cross B? A cross B is the set A, B, A, C, B, B, and B, C. Right? And that was from last time. How do we feel about that, 1 to 5? Okay. Now, this A plus B thing is the set, and it's a set. A, little subscript A, B with a little subscript A, B with a little subscript B, and C with a little subscript B. Now, the point is that I keep track of where the things came from if they're not distinct. The point is I made a new set where I said this was the B that came from here, and this was the B that came from here, the little b. In other words, I made them distinguishable. Okay. And this is called the cross product, and this has various unions. The most common one in math is to call it the direct sum. So whenever you use an alias to like give something a new name, that's kind of what you're doing. Where I want to keep track of where things came from, because it's important to, for whatever reason, to say, well, you know, they become distinguishable. Does that make sense? It's a little weird. As I said, it's not something that most people consider when they do math, but it is something that's a little important in databases because you can sometimes run into operations when you're doing this. And this is especially true when what you want to do is avoid the sieve. So if what you want to do is avoid computing all these things, you can actually play with this. And you want to because the size of A cross B equals the size of A times the size of B. And the size of A union plus B, or U plus, or cup plus, sometimes it's called, or the direct sum, is the size of A plus the size of B. And what we're doing is we're just making them distinguishable. That's it. Okay. We've got two more things. We've got things called the partitions. So let A be a set. Okay. I didn't get to functions. Oh well. Let A be a set. Yeah. I want to use, what color do I want to use? I want to use purple again. So I've had this like curly A, and what I've said, it's a collection of subsets of A, right? It's a subset of the collection. Okay. It's just a collection of subsets, okay? So, for example, A equals 1, 2, 3, right? I could have a possible A equals the set 1, 2, and the set 3. Does that make sense? 1 to 5. How do we feel about that? I just took a partition of these things. Not a partition. I took a subset of this. So it's not so much that I split them, although that will become the thing in a moment. It's that this is right. Another collection could have included the empty set. It's just all I've got is some subset of the power set. The collection A partitions A if for all, and I'm using a big X, for all big X and big Y in A, X intersect Y equals the empty set. Now, this is a very, very, very fancy way of saying that it looks like this. Oh, if there are two conditions. And X union Y, and let's just say A1. Dadgummit, how do I say this? And the union of all sets X in A, and A X equals A. Which is a very fancy way of saying that the pairwise intersections are empty. In other words, they don't cross each other. And they sum up to the whole thing. All right, I'm going to figure out a better way to say this that's not quite as mathy. But that's what you're actually saying. Okay, they sum up to the whole thing and they don't intersect each other. So look at the picture. All right, so for my example here, is it the case that 1, 2 intersect 3 equals the empty set? Right? There's nothing in between in them, correct? There's nothing in there together. There's nothing there. And it is the case that 1, 2 union 3 equals all of A. So this collection of sets is a partition of A. Here's how you think about it. I took X, I took Y, I took Z. I union them together, I get the whole thing, and they don't cross each other. Did that make everything nicely confusing? 1 to 5, how do we feel about that? It's a very simple concept that's very hard to nail down as a definition. Yeah. As a concept, it's simple. As a definition, it's a pain in the neck. Okay. So we got to partitions and what they are. I didn't quite get to Stirling numbers, but they're another example of the Sieve concept. And the whole point is we don't want to calculate how many partitions are in a large set. How many ways there are to partition a large set, because it's one of those things that are difficult to compute. But you can put some bounds on these things, which are nice. If you don't need an exact number, you can get nice things. We talked about union, intersection difference, cross product, direct sum, and we talked about partitions, but I talked about how to compute cardinality of those things. We talked about partitions, but I didn't talk about in-size partitions or the set of all partitions, which is kind of a pain in the neck anyway. So we'll just skip it. And next time we're going to start by talking about functions. Maybe the whole thing. Maybe we'll get finished logic. I wanted to get the functions, but move to next time. Are there any questions? I hate it when it does that. The notation, so this is just a curly A. I wanted something other than A. This is the power set. And that makes this collection A, this curly A, just a subset of the power set. Now, the important bit is the fact that this thing divides the set, where they don't cross into things. But we can't use the division symbol because we decided to use it for something else. Direct sum is one of those things that, okay, so the idea behind a direct sum is that if I know where things came from. So if I have something that's in both A and B, I create two separate things in the direct sum because I know that I relabel one of them. So I know where I actually relabel both. So I know where it came from, right? So my new thing has as distinct elements. They're not union. They're smashed in a sense. Okay. Also, so office hours tomorrow, I'm a little over time. Oh, well. Office hours tomorrow, I will probably be in the exact same place that I was last time. So that's on the loading dock behind the CMC building. There's a nice place to park. On my big fan. There's actually a nice place to plug in an extension cord. So that's why I want to be out there. So that's where I'll be as long as the weather's nice. If it starts raining, I've kind of scouted out a large inside room that I may be able to use. And then what I'll do is I'll open the door and stick the fan out the door if it's raining. So I may also have a foul weather spot for this. But you can also contact me between 12:30 and 1:45 is your time for Discrete. So you can and that's coding help. So I'll also be on Discord online for that help. I'm also going to try to get the problem set posted either tonight or tomorrow morning, so you can see problem set 3. Are there any questions about that? Yes, so I will be on Discord for coding. And then after that, I have general office hours. So the calc guys are not allowed to come to coding help, although I did tell one person. You will see, like, if you come, you'll see one person, like, running by, because then they have to go somewhere else during the regular office hours and they need to see me in person. But other than that, so I'm on Discord until 1:45. After that, I've got regular office hours from 2 to 3:30, and that's in person only. So I won't be taking, but if you want coding help, you can come then too, but you have to be in person. That one is in person only. And that's for both calc and everything. What does this say next to? Oh, the union is the whole set. Any other questions? All right. Can I do left and down? Did you get the area you wanted? The basement of the... Oh, you're talking about something entirely different. The CMC. So CMC is the building that is... if you know where the library is, and then you have that big, like, old runway type road, which is the, the wide one, the main entrance, and you go across from the library. There's 2 buildings there. One of them is one of the science centers, and if you go back toward the entrance to the university, toward Fowler, if you head south, you'll actually see CMC, and it's north of the engineering buildings, but south of the science and chemistry buildings. And I'm in the back. I'm on the Fowler side on the loading dock. So if you come in the automated doors that are closest to the library, just keep heading. Don't go to the stairs. Kind of go, and I'm right there out back. You'll see me. If you walk down the first floor of the CMC building, you'll see me outside. And then if there's rain, I'll announce in Discord where I am again, like I did last time. Okay, so that's it for today. Thank you for watching, and I will see, if I don't see you tomorrow, I will see you on Tuesday.